Hello, I am Gizem Mesci. In this video, I will give answers for the questions which were asked in the experimental video of the experiment 3. Let's start with the first question. This figure represents the single-core three-phase transformer. Here we can see that the leakage fluxes of the phases, like this. Actually, the transformer which was used in our experiment is not a large one, so these gaps are small. Therefore, it can be seen that the leakage flux of phase B is less than the leakage fluxes of phases A and C. The less leakage flux means the less leakage reactance, so we can say that because the leakage reactance value is less than in the phase B, the phase current of B phase will be slightly larger than the phase currents of the other phases. As a result, we can say that due to different leakage fluxes of the phases, the measured phase currents will slightly differ from each other. Another reason may be the third harmonic component of the current. In fact, the phase magnetizing currents in transformer should contain third harmonics in order to produce a sinusoidal flux. Delta connection of three-phase systems only allows the sinusoidal flux and voltage with no third harmonic current in the transmission line. However, the third harmonic components can flow within the phases. In other words, the third harmonics create a circulating current around the closed loop of the delta connection. Therefore, in delta configuration of three-phase systems, the phase currents may differ due to the third harmonic circulating current. Let's look at the second question part. By applying 2 wattmeter method, the total three-phase power can be measured by using two single-phase wattmeter. This figure shows the connection of single-phase wattmeter W1 and W2 to the Y-connected three-phase system. This single-phase wattmeter W1 measures the voltage between the R and B points and the line current IR. The second wattmeter W2 measures the line voltage between Y and B points and the line current IY. By using these two line current values and these two line voltage values, the total three-phase power of the system can be measured. In fact, this 2 wattmeter method can be applied on both Y-connected and delta-connected three-phase systems, and it can be also used for a balanced or unbalanced three-phase systems. In our experiment, in order to measure the load voltage, current and power, a wattmeter was connected between three-phase transformer and load. By using this wattmeter, in fact, the 2 wattmeter method was applied, and this is the connection diagram for this measurement. Here, while the voltage and current values of lines 1 and 3 are measured, line 2 is taken as reference. Because the current and voltage measurements of two phases are enough to measure total power of the three-phase system when we apply the 2 wattmeter method. Let's continue with the third question. In our experiment, the Y-connected secondary side of our transformer was connected with the Y-connected load via wattmeter. The neutral connections of the load and the secondary side of transformer was separate from each other. The question is that what would be the effect of having a connection between the neutral points of the secondary side of transformer and the load? The balance laws are designed in a way that each phase has the same impedance, so if they have the same voltage across each phase, the current will also be the same. In a balanced three-phase system, when all currents and their power factors are the same, the phasor sum of all line currents is 0 ampere. Because of this reason, there is no need for a neutral wire connection between the balanced three-phase systems. However, if the load is unbalanced, the load doesn't draw the same current in each line. In this case, the currents don't balance out and there is some left over. This is the out of balance current. In fact, to carry this leftover current to the supply is one of the purposes of the neutral wire connection. In unbalanced load case, without the neutral wire connection, all sorts of instabilities occur in the system, like unstable voltages and unexpected currents. Another effect of connecting the neutral points of secondary side of our transformer and load may probably be to eliminate distortion in the load phase voltages. If the flux in the magnetic core has sinusoidal waveform, then it will give sinusoidal waveform for the voltage, and the sinusoidal waveform of flux requires a third harmonic component in the exciting current. Actually, we can observe this in this graph. This is the distorted waveform, and the purple one is the third harmonic component, and the red one is the fundamental wave, actually a sinusoidal wave. If the neutral points of the Y-connected three-phase systems are not connected, then the third harmonic component cannot flow. As a result of this, the flux in the magnetic core will not be a sinusoidal wave and the voltages will be distorted. In other words, if the neutral point of load is connected with the neutral point of the secondary of our transformer, the third harmonic component of the current can have the path to flow and go to the supply. Because we know that in our experiment, the secondary side of our transformer is connected with the primary side and primary side is connected with the voltage supply via wattmeter, so the third harmonic component can flow into the supply and the sinusoidal voltage form can be achieved by connecting the neutral points of the secondary side and the low side. Let's continue with the fourth question part. Resistive load elements convert electrical energy into heat using power resistors. Inductive load elements store the energy in the form of magnetic flux when current flows through them. And capacitive load elements store the energy in the form of charge. In fact, we know that the average power, or we can say the real power of a resistive element, is greater than zero. On the other hand, the average power is zero for inductive and capacitive elements. By function, resistive load elements generate large amounts of heat. This heat must be quickly dissipated from a load bank to prevent overheating. Consequently, resistive load banks use forced air cooling, which is provided by a dedicated power circuit and one or more blowers. And here there is a fan on the resistive load bank. On the other hand, when compared to resistive elements, inductive and capacitive load elements generate very little heat. Consequently, convective cooling or a small fan is sufficient for most of them. In some inductive and capacitive load bank designs, a fan is not even needed, as with the reactive load banks which were used in our experiment. Now let's look at the fifth and the last question. When we supply a real power to the primary side of our transformer, this real power will be equal to the total power losses on the secondary side of our transformer and on the RL load. In the two-stage resistive and two-stage inductive load case, the total power of primary side was measured as 432 watts. On the other hand, in the 2R and 3L load case, the total power of primary was measured as 467 watts. In this part of the experiment, the reason for this difference between two power ratings were asked. In fact, the power losses on the secondary side of the transformer are due to the copper losses and the power losses on the load are due to the resistive elements. Actually, the change in power is not because of the resistive elements of the load, because we know that the power loss on a resistive element can be found with this formula. Here the equivalent resistance R does not change between two cases, and from datasheet of this experiment we can say that the voltages on these resistive loads are more or less the same, these values. Therefore, this V square over R ratio is almost the same for resistive elements of the load. In the case of 2R and 3L load, the impedance value decreases because of the fact that the equivalent reactance value decreases with increasing number of parallel connected inductive elements. We can observe this result from this equation. This decrease and then the impedance also decreases. In other words, in 2R and 2L load case, the equivalent resistance is R over 2 and the equivalent inductance is L over 2. While in 2R and 3L case, the equivalent resistance is still R over 2, but the equivalent inductance is now L over 3. As we know, the decrease in impedance value will cause the increase in secondary side current value. As a result of this, the copper losses increases because in the secondary side, the current flowing on the copper increases. In fact, this is the reason for the increase in total power of the primary side of our transformer. This is the end of the video. Thank you for listening to me.